Hello and welcome back to Calculus 3. We are starting chapter 13. This is the chapter on integration. We are going to deal with double integrals, triple integrals. You will see that you can actually have any number of integrals you want. We are going to see that you solve them from the middle integral out, right? So you go to the inside first and you go out. And then you have to worry a lot about dx, dy, dz and stuff like that, because those will tell you which variables are your independent variables and which variables will be kept as constants or parameters as you integrate. So that's very important. Before we go into any of the Calculus 3, I have to go back to Calc 1 first and deal with certain things. So now, first of all, when you have a function, let's say it's square root of x, whatever it is, you will integrate that function between points a and b, right? The points a and b, by figuring out the integral a to b of f of x dx. Now, why are all these things important? Well, dx over here is very important because that's going to be the width of what we would call representative rectangle. So it will have the width, delta x, right? Now, delta x is the width, and you can see the top over there is the height is the function. So function times delta x is going to give you that area, and then you work on all of them. So this integral is actually s, and s stands for a sum, right? So all of that stuff is that, right? Sum of all delta x's, right? So of all delta x rectangles that you have. So what you are going to have here are infinitely many of these rectangles, and each one fits under a point. And when you add them all up, you add all of these rectangles, and you get exact value. So that's what we have in Calculus 1. The integral a to b of f of x dx, as I mentioned, is you first take your function f of ci times delta x, which is the one rectangle, and then you add many of those, and then you send that number to infinity. And that is what we call Riemann sum. So you have one rectangle here, then you have all the rectangles there, and then you eventually send everything to infinity. So you have infinitely many rectangles to add up. Now those rectangles all add up to the exact area of under the curve, and you have your definite integral. So now what's important for us to understand is that we have our domain to be AB. So it's a one-dimensional domain, right? It's the interval AB. Interval. And that interval is actually x1 and x2. So both are x variables. So now, when you rewrite this, you get x1 to x2 of f of x dx. So what you see is what I say, x, 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 right? You see all of these to be x's. So they're all x variables. You have x values on the interval from x1 to x2. The function is in terms of x, and then times dx. Now you must have dx as well, because as I said, this is going to give you height, this is going to give you width. Height times the width is the area of the single rectangle, and then this integral is the sum that represents the infinitely many rectangles added So now we have all of them added, and we get what we are looking for, which is the area. Now I'm going to move to Calc 3, and I'm going to add another integral on the outer shell. So what I'm going to have now is the integral f of x, and then I'll put dx and dy, let's say. Now if I put dx and dy, these limits over here better be y1 and y2, because they correspond to the outer variable, and then the ones on the inside, x1 and x2, which is the good old dx correspondence. So all I did is I took what I knew before, which is this integral, this integral here. This is the old integral, so if you just focus your eyes on what's circled, you will see your Calculus 1 integral, which I just described earlier. And you see that I added another integral on the outside. So this means that I should be able to completely solve the integral inside first, and then just add the integral on the outside when I have the inside solved. And this is how you solve these double integrals. Later on, for triple integrals, I'm just going to add another one on the end. Maybe z1 to z2 dz. Then I can add another one, dw. Then I can add, you can put 50 integrals if you want. You will always do the one that is most inside, right? And the limits have to be from that variable. So if the first one is dx, your values are x1 and x2. If the first one is dy, which it could be, then it's y1, y2 on the first integral. So what's important is the stuff that I did underneath, right? The variable for the input variable, right, for in your domain, for dx and the interval have to match. That's the requirement. Now, which order of those you are going to have, well, that depends on what we get as we go along with the integral. Now, what is actually happening here? Well, note now that I have three things that are multiplying. If I have three things, I have f times dx times dy, well, that's 3d, which means volume. So a double integral with a function inside is going to compute volume. So something like this computes volume. The shorthand notation for this would be double integral of fx, and then you put dA. Because dx times dy, well, x times y is the rectangle, is area, right? So the shorthand notation for this would be double integral fx dA. It could be dx dy or dy times dx, whatever. So it's one or the other. That's what dA is.
Why the capital notation?
Capital, well, A is generally, right, capital letter. If you put lowercase a, generally it's either a parameter or side of a square or something, right? So we keep x and y lowercase. Those are the distance in x and distance in y. When you multiply x times y, you get the capital A for area. So this A actually is area over here. Now what do I have? I have a length, which in this case is upper. And, oh, guys, this should say now fx comma y. Yeah. Function can be in both of these variables. So x comma y. Ah, this one as well. Holy nightmare. So now to take a look, before we go more into details and theory, let's take a look at a vanilla example. Let's say you have 1 to 3, and you have 2 to 4, whatever, of x squared y minus 3x dy dx. So this is the problem that I want to look at. So, mechanics of the problem. As I said, deal with the inner integral first. Observe that y value is your variable, which means x variable is to be treated as a constant, which means you get to copy it. If it was a derivative, that 3x would die, right? But now it's integration. So that 3x over there is a constant, so when you integrate it, it will pick up y. You have to copy the outer integral, the one that you haven't used yet. And inside you're getting x squared, y squared over 2. You are copying x squared, that's a constant. Integral of y is y squared over 2 minus 3x y, computed from 2 to 4, and you still have dx to deal with. So the outer integral, right, the integral 1 to 3 and dx, that hasn't been dealt with yet. The inside integral in respect to y is what we calculated. So this is me plugging in regular f of a, b minus f of a. All of that in parentheses dx. So now we have to compute this. I have 8x squared minus 12x minus 2x squared plus 6x. Oh, and we don't put plus c or anything as we are going to this because it's a definite integral, right? All right, so when this combines, I have 6x squared minus 6x dx. And there's your Calc 1 standard integral that you have seen in Chapter 5. You are going to integrate this now. You get x squared over 2, computed from 1 to 3, for a total of, well, 6 and 3 will cancel. You get 2 times 3 cubed, minus this also cancels, 3 times 3 squared, minus 2 times 1 cubed, plus 3 times 1 squared. That's 2754 minus 27 minus 2 plus 3. That's 27 plus 1, 28. Get 28 at the end. Because it's basic Calc 1. You should be able to do it. So what I have done is I computed the inner integral first, and the function ended up being in terms of x, and then I integrated x out, and because it was definite integral, I was able to compute to get 28 at the end. So now you have your integral, double integral. This is the first double integral solved in the class, right? And you've seen that it's basically 2 calculus 1 integrals done. It's just nested. So you do the inner integral first, and then the outer integral. Once the inner one is solved, you do the outer integral, whether it's definite or indefinite, and you get 28 at the end. Next. Now we have to discuss more about this integral. So we had integral 1 to 3, 2 to 4. Over here, I'm just going to put fxy. It doesn't matter what's in here. And then we had dy and dx. And in the blue corner, we have our good old integral, let's say 3 to 6 of some function f of x dx. Remember what I said about the input. You have some region. Well, now this thing over here is going to be region in 2D, in R squared. And we can graph that region if you graph that region. You see that your x is between 1 and 3. So that's what 1 is and that's what 3 is. There's 2 in between, right? 4 and so on. And you see that your y values are between 2 and 4. So what you have here is region R. This is your region R. We are integrating over the region R. And that region is in 3D. In 2D, sorry. So, guys, this XY graph that I have here is the floor of the third-dimensional realm. So what I have here is the region R. So now there's going to be some kind of a surface over here. This surface is governed by fxy. And what happens is now I'm going to have a stencil. Right? Because this object on top, right, which extends all the way down forever to the xy plane, this is going to cut an object like this. The imagery that you should have in your head is you take the cookie dough stencil, right, the cookie cutter, and you press that into a dough. What do you get? Well, whatever the shape of a stencil is, in our case for this lecture, the stencil is always rectangular. Whether it's a square or a rectangle, whatever it is, the stencil is always going to be boring, right? You know that you know, if you're making the Valentine cookies, the stencil is in the shape of a heart, right? So your region R is in the shape of a heart. You can have the flowers and the little pretty people and whatever the stencil is. That stencil, right, that shape that you have, that's going to be in the xy plane, the region over which you are integrating. And your walls are going to go straight up to meet the surface of the object. So this is technically what we have as a stencil. Now, we pick a representative, I call it a representative French fry, right? In this region, we pick a representative French fry. So, over here, representative French fry, because that's exactly what it's going to be. It's going to be a little representative French fry over here. It's going to go up all the way to the surface to give us little representative French fry. So that's what it is. Representative French fry. If you take a look at the representative French fry, it will have dimensions, delta y and delta x, which are your dx and your dy. And it's going to go up from there. The height is going to be at fxy. I hope you see and you know that the representative french fry has a volume because you eat it, right? You eat the french fry. It exists as a 3D thing. So, next time you're at a place with a french fry, obviously you're going to take one french fry and stand it up on your desk. And then whoever is with you, you're going to explain the delta x on one side, the delta y on the other side. And then you might group 5 or 6 french fry together and explain that the shape they create on top is fxy. And if you are to compute each individual volume of each of that french fry, they all add up to the volume of the whole bunch, which creates the shape. This is why I eat alone. Which is good because I get to eat all of the food that is presented to me. All right? Which makes me the man I am today. So when you look at the french fry, right? When you look at the french fry next time, think of this. You will see that the french fry on the top is never flat. French fry is rounded because the potato out of which the french fry was cut is not a box. It's round. It's almost elliptical, right? Ellipsoid, like a watermelon, right? So it's going to have some curvature on the top. That curvature on the top is supposed to follow the curvature of the shape. Because what is the volume, right? If I say this, I put this on top, right? What's the volume of this thing? Right? Well, we have calculus. Ooh, magic. Look at that. It? Right? There's another one, but then you have, if I remove now, the social justice warriors are going to go crazy. Anyway.
So the red line does not represent delta z, right?
Yes. So the red on top is going to match the surface of the top, where some french fries will be shorter and some will be longer, and so on to the best approximate the height. Then, as they approximate the height, the smaller and the thinner you make the french fry, the better approximation you have, because there will be less error. When the french fry is thinner, it will fit better to the top, because it will have smaller surface area to fit. So it's the same thing like in Calc 1. The thinner your delta x was, the less error. Now the thinner the french fry is, less error. Now this is a completely different conversation. This one is supposed to have at ShopRite, talking to the person working there, because they have all different types of french fry, thinner and thicker, right? Usually at the restaurant they only have one kind, so it's really not a story for the restaurant to talk about how good your approximation is. But when you're a ShopRite or whatever other place that sells food, you have bags, and you see all right those very, very thin french fry boxes and bags, and those they're very thick. So now, the thinner the french fry is, the better approximation, but for the same volume to cover, when you have thinner french fry, you will need more of them, right? So having more french fry means having more calculations. So there's a trade-off there, right? You might want to invest a little bit more work to calculate a little better result. But then you don't want to go and really calculate 10,000 french fry units, right, to approximate something to the 15 decimal if you don't need the 15 decimal precision. So as engineers, you make the decision on what is the precision you need, and then you set the parameters in your software to do it, right? You're not going to sit there, calculate this by hand on the calculator from 1987. So now, it will be good to take a look at some of the images provided in your $250 book. This is why it's so much. I'll give you this. So there's the actual shape, and there is your French fry representation of it. So this is what you're supposed to get when you put all of the French fry together. If you want to really have some cool stuff, play Minecraft. You can do that in Minecraft. And yeah, my 5-year-old is almost there. Here is another image. This is what I was trying to draw, where you have the grid on the floor, on the XY, which cuts out with a rectangular stencil for this lecture. Right? Next lecture is general stencils. So you're going to have anything goes, right? Now it's just rectangles or squares. Well, square is a special rectangle, so rectangles. And you see the bottoms of each one of the, and here's your representative French fry, right there. And you see the top is flat, but it should assume the curvature, right? And approximates that curvature. So the more French fries you use, the better approximation gets. So over here, what do you have? 16 French fry. Over here you have 64 French fry. Over here you have 256 French fry. This is technically like spaghetti, all right, or whatever. Going into the angel hair and stuff like that, which are all the projects that the Math Club actually did in the past. Yes, they entered the competition for spaghetti bridge. The engineering club challenged the Math Club because Math Club was doing all of these projects and constantly bragging that they're better. Engineering club, how about the spaghetti bridge competition? All you're allowed to use is spaghetti and the Elmer's glue. No linguine. That was one of the rules, right? Math Club said, challenge accepted. Destroyed them, both years. Destroyed them. Absolutely, third year, they didn't get invited. They did not invite Math Club third year. These guys, I have both of the winning bridges in my office. They're both broken, obviously, because that's the way to test them. You put them in between the two desks. You hang the piece of rope and the bucket, and then you keep adding weights until the bridge breaks. And when the bridge breaks, that's the weight you can carry. And then the weight of the bridge divided by the weight it broke gives you the coefficient of how much bridge it can withstand. And needless to say that the bridges are on average 15 times stronger than the ones presented by Engineering Club. But again, hey, strength in numbers. What do you think is stronger, this or that? If the material that creates these is the same and you're using glue. Right? So that's how they win, right? We know how to deal with these kind of things. Obviously, always should win, but that's okay. So now you understand the concept behind all of this. Please note that your base, the stencil, the cookie cutter, is always rectangle. In our case, it was 2 by 2 square. It just happened to be because I picked whatever numbers, and yeah. But it can be any kind of a rectangle as well. So that's that. And then finally, the double integral definition, which we are going to write, where you have the double integral is equal to the sum of your function is the height, and delta A is going to be on the base, any of those small rectangular areas, which is the base of the French fry. So you see that the definition for it is exactly the same as Calculus 1, except now we have 2 variable input, and this is the area at the other end. So let's write this definition, and then just work out some integrals and be done with this. So simple. So looking at this picture, we have the definition. So I'll just put this over here to be dA, right? And we'll say that the double integral over region R of f of xy dA is equal to the limit as delta goes to 0, meaning delta x and delta y, for the summation where I goes from 1 to n, for f of xn yn times delta a n. So this, when you say n, it's a representative one, and then you have to add all of them and then infinitely many of them to add all of them for the volume. Now, the next story, I'm going to deviate a little bit from the book because I don't think they describe this in a greater detail, is the understanding of dimensions. So I did mention earlier, when you have integral a to b of f of x dx, you are calculating area because you have 2 dimensions. With a double integral now, from let's say a to b and c to d, f of xy, and then I have to do now dy dx because I put a and b on the outer side, I have 1, 2, 3, and that's a 3D, which we know it's a volume. So it's very important to understand these dimensions. Now, double integral a to b, c to d of dy dx is equal to what? Area. Beautiful. No function. So you only have 2 dimensions in here, and dy times dx is giving you area. So double integral can give you area or volume. That depends whether or not you have the function present in the integral or not. Now let's take a look at the interesting calculation here. This is one of those stories, let's say you are tutoring a kid, right? And the area of the rectangle came up, and you said, oh yeah, it's just a times b, and the kid goes, why? Ooh. Let's see. So you draw a random rectangle, and this rectangle, as you can see, is 2 to 8 and 1 to 3. And then, since you explained already last time with a single integral and the kids still say why, it's time to explain with a double integral now. You raise the stakes, right? So, what is the area of this rectangle given the double integral? Well, you pick whether you want dy dx or dx dy. Now, if you pick dy dx, outer integral is x, and the x values are 2 to 8. And the inner integral is y, well, the x values are 1 to 3. So now, what you have is the inner integral calculated first. So copy 2 to 8 integral, and then you're integrating 1, so that's just going to be y, computed from 1 to 3, and you still have your dx. So now this is going to be integral 2 to 8, and then you have 3 minus 1 dx, which is integral 2 to 8 of 2 dx, which is 2x computed from 2 to 8, which is 2 times 8 minus 2 times 2, which is 16 minus 4, which is 12. If there is still doubt, well, let's count the number of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The area turned out to be 12, and the number of squares is 12, so mathematics still holds for today. Bueno? Perfect. So now we have that, and we've shown that the area of this rectangle is 12. Now I want to compare that to the previous life. Remember the area between two curves? Yeah, you do remember area between two curves. Here in green you have the integral of f minus g dx, right? The top minus the bottom. Let's set it up. That's integral 2 to 8. The upper function is 3. The lower function is 1 dx. That sounds familiar. Have I seen that before? Of course, it was a step in our calculation. Don't you agree that calculating definite integral is f of b minus f of a, right? Well, here is your f of b. Here's your f of a from the inner integral. Right? All right. So this is all connected. And it will make much more sense the next time. Ooh, this can be an alien.
It's like an ant. Yeah.
All right, fine. That's enough of that. It's the reason why you're paying $4,000 for this course, right? At RPI. They don't draw these things. All right. So now we understand that, and let's see what other cool things we can do. So as I mentioned at some point, like we're 5,000 times so far, your job when you start working is not to sit and compute these integrals. No one can care less about it because we have software that we pay and the software computes it. And it's only $2K to buy the software, so yeah, right? Much cheaper than you, right? Right? You're selling 4 problems out of 60 that are posed. You have 4 problems that are actually useful to you for your relevant work experience later. And here's a skateboard ramp, or whatever this is. It has a shape of e to the negative x, so it's going to be, when you look on the side, it's going to be curved, right? It's a skateboard ramp, or the, you know, whatever, the bicycles and motorcycles and whatever you have and jump around and fun, right? So there's a surface. What's the volume of this thing, right? If it's going to be solid material, maybe made out of concrete,